Inside a human joint, an orthopedic implant made from ultra-high molecular weight polyethylene will endure millions of cyclic loading impacts. At this scale, tiny variations in the factory temperature dictate whether a component survives for decades or fails under stress. For years, engineers have optimized this injection molding process through empirical trial and error. You adjust a dial, you mold a batch, test until it breaks, and repeat. In a high-stakes biomedical context, this process is slow, resource-intensive, and prone to blind spots. By applying machine learning to experimental datasets, we can map exactly how processing inputs dictate mechanical outputs. This allows for the translation of physical observations into a predictive quality control protocol. Aligning these specific parameters with a trained model allows for the definition of a consistent manufacturing envelope. It targets the specific microstructural integrity required for decades of physiological durability. This sequence shows the baseline injection molding workflow. We start with medical-grade UHMWPE pellets, push them through a micro-injection molding machine, and stress test the resulting physical specimens. The mechanical yield on the right is traditionally viewed as the product of a highly complex system. Engineers have to balance injection pressure, holding time, mold temperature, and cooling duration all at once. The data simplifies this equation. When we run these variables through an ensemble machine learning model, melt temperature emerges as the overwhelmingly dominant factor. It drives nearly 90% of the ultimate tensile strength and 74% of the material's stiffness. Conversely, adjustments to holding times and cooling durations barely register. Their predictive correlation approaches zero. Identifying melt temperature as the apex variable completely restructures the optimization workflow. You stop dividing your attention across secondary dials and concentrate your capital investment on precise thermal control. To understand exactly how melt temperature dictates these physical properties, we use SHAP analysis, a framework that attributes specific prediction outcomes to individual input features. This histogram tracks the ultimate tensile strength of our molded specimens. Rather than a flat, continuous line, the material exhibits a bimodal distribution with two distinct peaks. Processing the polymer at melt temperatures below 230 degrees Celsius creates a highly crystalline internal structure. This high-density crystallization generates the peak on the right, pushing the material up to 42 megapascals of strength and maximum stiffness. Pushing the melt temperature above 260 degrees restricts crystallization and increases the amorphous phase of the polymer. The overall strength drops down to this lower peak, near 30 megapascals. However, that drop in raw strength yields a massive gain in ductility. As panel C shows, those same high-temperature specimens stretch up to 60. This chart shows the predictive accuracy of our random forest model. The tight clustering of data points right along the diagonal line proves the algorithm successfully maps physical manufacturing variance to mechanical outcomes. Looking at the residual errors, we see a narrow, zero-centered distribution. This provides an empirical 95% prediction interval. We know the likely range of mechanical fluctuation based on the thermal drift of the machine. Armed with this confidence interval, engineers can dial in a processing temperature that ensures every single part will clear the strict 30 megapascal ISO baseline, accounting for expected factory floor fluctuations. Uncertainty quantification cages the inherent chaos of the molding process inside a defensible mathematical boundary. Taking these data models back to the physical hardware dictates exactly how we set up the factory floor. The highest return on investment comes entirely from thermal regulation. Facilities must install precise thermal sensors and tightly calibrated heating bands to control the melt temperature. The production loop becomes highly targeted. You set the exact melt temperature, run a test batch, and compare the physical yield directly against the machine learning confidence bounds. During mass production, the continuous sensor data acts as a real-time monitor. It flags subtle thermal drift before that drift alters the crystalline structure of the polymer. This continuous feedback loop ensures every raw pellet receives the exact thermal history necessary for compliance. We have transitioned from empirical trial and error to a system of calibrated probabilistic modeling. By translating physical tests into trained ensemble models, manufacturing outcomes move within defined, mathematically bounded ranges. The data confirms that precision control over melt temperature is the highest priority intervention for ensuring consistent biomedical reliability. Before initializing an orthopedic production run, audit your thermal variance. Ensure your hardware can maintain the tight tolerances the data demands. Locking down melt temperature is the singular key to locking in decades of clinical durability for the patients who rely on these components.